Hello, good morning. I will discuss about corrosion in this lecture. I am Dr. Abhijit Shaha from Chemistry Department. I am taking BTech Chemistry course. Today we will discuss on what is corrosion, what are different type of corrosion, and finally we'll discuss Pourbaix diagram of iron. These are the three important topics for your syllabus. So first, what is corrosion? Corrosion means it is a very common thing we always see in our in in our environment. We have seen that rusting of iron. If we keep one iron rod outside, we can see after a few days rust formation on its surface. So this rusting is a part of corrosion. So corrosion is mainly a destruction or deterioration of the metal start at its surface because of some chemical reaction with its environment. It can be direct chemical attack or electrochemical attack. So by definition, what is the definition of corrosion? Definition is corrosion is any process or deterioration or destruction consequent loss of solid metallic material through unwanted chemical or electrochemical attack by its environment starting at its surface. Corrosion is always started at the surface. Example, rusting of iron. Now, why corrosion occurs? Actually, all this metal, whatever we are using, like iron, copper, or silver, any metal, gold, okay. So, in our earth, it is not present as a pure metal. It is present in form of some oxide or sulfide or carbonate, right? Those forms we are converted by reduction. Right? If we have if let's say for example iron, in iron is not present in form of iron, means Fe in our nature. It is present like iron oxide. So we are taking out this ore from our earth and then we are performing some reduction reaction. So iron oxide, iron is present in iron 2 plus. If we perform reduction reaction, it will form iron rod. So this reaction, it is not spontaneous. Means so we are converting iron 2 plus to iron. This iron 2 plus to iron, this process is not thermodynamically spontaneous process. However, iron to iron 2 plus is thermodynamically spontaneous process because in nature iron is present as an iron oxide. So naturally, when an iron rod is present outside, it is always tends to form iron oxide or other uh, materials. Basically, it is trying to convert iron to iron 2 plus. So it is a natural process. It is a thermodynamically spontaneous process. So corrosion is a thermodynamically spontaneous process and gives free energy change of the corrosion. It will be negative. Okay. So this is the basic idea of corrosion. Okay, what is corrosion? Corrosion is a thermodynamically spontaneous process. It starts at the surface of a metal, and it is occurs because of chemical or electrochemical attack. An example is rusting of iron or formation of green film because of copper hydroxide or copper carbonate at the surface of copper metal. Okay. Now, type of corrosion. Type of corrosion means it can be two types. One is dry corrosion, another one is wet corrosion. Dry corrosion means uh, without any solvent, without any solution. That is called dry corrosion, chemical corrosion. Wet corrosion is with some solvent or with some solution. Corrosion in some solution. That is called electrochemical corrosion. Means the corrosion in our electrochemical cell. Okay. So we'll discuss these two type of corrosion. First, dry corrosion. Dry corrosion can be three types. One is oxidation corrosion, means corrosion by oxygen, corrosion by other gases, that is called and corrosion, liquid metal corrosion. Okay. So first we'll discuss this dry corrosion and then we'll discuss the electrochemical or wet corrosion. So first type of corrosion is oxidation corrosion. Corrosion by oxygen. So directly oxygen is present in our air. So when oxygen is interacting with metal surface, it forming some metal oxide, that is called oxidation corrosion. It can occur at low temperature if the metal is very much oxidizable, like lithium, sodium, potassium, rubidium, beryllium, calcium, strontium. So very low temperature this oxidation process start and forming and this corrosion start. Okay, some metal which are where oxidation process start at little high temperature. Okay, for example, iron. It is not started at low temperature, it started at high temperature. And there is some metal which is less susceptible to this corrosion. For example, silver, gold, platinum, this type of metal we are using as an ornament because those metals are not corroded because their oxidation process required very high temperature. Okay, so corrosion, oxidation corrosion is corrosion by oxygen. Uh, Now there are three important reactions in this corrosion. First one, first reaction, that is oxidation of the metal. So metal will release the electron and forming metal plus, right? If a number of electron is released, then it will form a metal N plus. Now this n number of electron will goes to oxygen, which is present in our air. So when oxygen is taking this electron, it is forming oxide. Now this metal plus and oxide, they combine and forming metal oxide. So these are the three basic reactions of oxidation corrosion. Now corrosion by other gases. So not only oxygen, other gases can corrode a metal. For example, if we talk about chlorine gas, okay, so chlorine gas can react with tin can form stannous chloride, SnCl4. That is called SnCl4, and in that way, tin material actually degraded. Hydrogen sulfide, it can form react with iron and can form iron sulfide, right? Chlorine can also react with silver, forming silver chloride, right? So these are the some reaction by which other gas can corrode some metal. Next one, corrosion by liquid metal. We know there are some liquid metal, for example, gallium, for example, mercury. They are the liquid metal. Now, when we put this liquid metal on some solid metal, for example, if we have sodium metal and if we put mercury on it, we'll see that sodium metal, that liquid metal penetrate into the solid metal and destroying the solid metal. That is also one type of corrosion. If we put mercury on sodium, we will get sodium amalgam. So in that sodium amalgam, actually sodium metal is corroded. If we put gallium is a liquid metal on aluminum, we will see that aluminum shell will be completely destroyed. Right? So this is called liquid metal corrosion. Okay. So what we discussed till now, we discussed what is corrosion. Then I told corrosion is a natural process, spontaneous process, thermodynamically spontaneous process. Delta G will be negative. We discussed about two important type of corrosion: wet corrosion and dry corrosion. In dry corrosion means corrosion without any liquid. In dry corrosion, there are three types: oxygen corrosion by oxygen, oxidation corrosion, corrosion by other metals, other gases like sulfur dioxide, chlorine, right, hydrogen sulfide, and last one, liquid metal corrosion. Okay. Next one we'll discuss that wet corrosion or electrochemical corrosion. In our electrochemical cell, there is a cathode and there is anode. In anode, we know that metal is converted to metal in plus and electron. So when metal is converted to metal in plus, means anode is converted to metal in plus. So some of the metal is now coming into solution. So with time, that anode will the means some if anode is a metal. Now in anode, from anode when metal is coming into solution, so anode will be corroded, right? So that is called electrochemical corrosion. So in electrochemical corrosion, it started electrocorrosion start at anode, right? Now electrochemical corrosion, there are two important reactions. One is anodic reaction, cathodic reaction. In anodic reaction, we have seen that anode material actually oxidized. In cathodic reaction, what are the reaction? In cathodic reaction, there is a two type of reaction. One is evolution of hydrogen, another is absorption of oxygen. Okay. In anode reaction, there is only one reaction, that is anode material is oxidized. Metal is oxidizing to metal N plus. Now that electron is coming to cathode, and after coming, that electron is for making two reaction. One is evolution of hydrogen, another one absorption of oxygen. So cathode reaction is two type: evolution of hydrogen and absorption of oxygen. Now first is evolution of hydrogen. Evolution of hydrogen reaction is, so first is this is our anodic reaction. If we take iron is our metal, so iron is converted to iron 2 plus 2 electron. Now this 2 electron is coming to cathode. In cathode, there is a two hydrogen H plus ion in solution. This two H plus ion will take hydrogens and forming hydrogen gas. So hydrogen gas is forming and evaluated. So it is called evaluation reaction, hydrogen evaluation reaction. So overall reaction is iron plus 2H plus, iron 2 plus hydrogen. And absorption of oxygen, and there is some oxygen, dissolved oxygen in solution. Now this oxygen will taking two electron forming hydroxide, right? Now this hydroxide is forming, so this hydroxide formation is an oxygen absorption reaction, right? So overall reaction is iron 2 plus in presence of oxygen is forming hydroxide 2 OH minus, giving FeOH whole 2. Now if there is enough oxygen, then a FeOH whole 2 is further oxidizing to FeOH whole 3, that is forming yellow rust. Okay. If oxide, if supply of oxygen is limited, then we are forming another oxide Fe3O4. Fe3O4, there is a iron is present in two different type of oxidation state. One is iron 2 plus and another one is iron 3 plus. Both oxygen state is present here in Fe3O4. Okay. So overall oxidation number of iron in Fe3O4 is 2.66. It's not 2, it's not 3. Okay. So this is about the electrochemical or wet corrosion. So what we understood in electrochemical corrosion, there is some occurs in electrochemical cell. In electrochemical cell, there is anode and cathode. Anode means always some metal. So metal will be corroded. So during corrosion, metal is forming to metal oxide, metal plus, and the electron is coming to cathode. In cathode, it is forming hydrogen evaluation reaction and oxygen absorption reaction. So after oxygen absorption reaction, it is forming it's forming hydroxide. So iron 2 plus reacting with OH minus, forming FeOH whole 2. If the supply of oxygen is more, then it will form FeOH whole 3 when iron is present at plus 3 oxidation state. In FeOH whole 2, iron is present plus 2 oxidation state. And now if the supply oxygen is limited, it is forming different type of oxide called Fe3O4, where iron is present at plus 2.66 oxidation state. Okay, it is not plus 2, not plus 3, it is in between. Okay. Now last one in our corrosion topic is the Pourbaix diagram. It is very important. Pourbaix diagram is, so when iron is corroded, right, it is forming, initially iron is present iron in form of iron. Now if it is corroded, it is forming iron 2 plus and then iron 3 plus. So these are the different electrochemical state of iron. Now how this electrochemical state is depends on the pH of the medium, that is described by this Pourbaix diagram. So in Pourbaix diagram, we have the y-axis the potential and the x-axis the pH. Now, if we change the pH, how this potential and this reaction is changing, that will be discussed in this Pourbaix diagram. Okay. In Pourbaix diagram, there will be three different type of different type of what is called zone. First one is there is iron. This is called actually protected zone. Iron 2 plus and to this pink color it's called corroded zone, corrosion zone, and this green color is called passivation zone. So when it is forming, when it is present in iron state, okay, so corrosion not started still now, that is called protected state. When corrosion is occurring, so corrosion state. And when it is forming some oxide, iron 2 oxide Fe2O3, iron 3 oxide Fe, sorry, Fe2O3, iron plus 3, and another oxide Fe3O4. When it is forming this oxide, it is called passivation zone. So Pourbaix diagram is a plot of Pourbaix diagram plot the electrochemical stability for different redox state of an element as a function of pH. Okay, this diagram essentially phase diagram that map condition of potential and pH in aqueous solution where different redox species are stable. Okay, this diagram is given at room temperature, at normal atmospheric pressure, and molar concentration 10 to the power minus 6. Okay, now this is in this diagram there will be 5 different reaction. First reaction, iron to iron 2 plus. So now you can see in this reaction is electron dependent. Okay, potentially pure redox reaction. In this reaction there is no H plus ion is involved, so it is no pH dependent. Another reaction, iron 2 plus to iron 3 plus. This reaction is also pure redox reaction because pH is not involved, H plus is not present, right? So first these two reaction is pH independent reaction. Okay, redox dependent and pH independent reaction. Okay, next reaction is iron uh, iron 3 plus to iron oxide formation. Okay, iron 3 plus to iron oxide formation, Fe2O3 oxide formation. Now if we in this reaction we can see there is H plus ion is involved. Iron 3 oxide, iron 3 plus to iron 3 oxide, Fe2O3. Here iron is present plus 3 oxygen state. So this side and this side, both side iron is present in plus 3 oxidation state. So there is no redox. There is no change of the electron. So it is not a redox reaction. However, it is pH dependent. Why? Because H plus ion is present here. So if we change the pH as per Lars-Letellier principle, so H plus ion, as if we change the pH, H plus ion will be changed, concentration H plus ion will be changed. So reaction means forward and backward reaction, it can vary. So if we so this reaction is pH dependent. Now we have also iron 2 plus. Now iron 2 plus can also form another oxide, iron oxide, right? So this is another reaction. In this reaction, okay, in this reaction you can see iron 2 plus to iron 3 plus is forming. So here iron 2 plus is present, here this iron is 3 plus is present, and also in this reaction H plus is involved. So this reaction is both pH dependent as well as redox dependent, right? One more reaction is present here, that is Fe2O4. Okay, this is another reaction. There will be Fe2O4 to H plus. There will be another iron. Oh, by mistakenly it is not written. So in this reaction 5, it is also pH dependent as well as redox dependent. Okay, so in Pourbaix diagram we have 5 reaction. First 2 reaction uh, will be redox dependent, no pH dependent. Third reaction will be pH dependent, redox independent, and fourth and fifth reaction will be both pH dependent and redox dependent. So now we will see this diagram. So this is our diagram. In this diagram, x-axis showing the y-axis, it is showing the potential, x-axis it is showing the pH. Now first iron is present. Now if we increase the potential, it is converted to iron 2 plus. So this line 1 Okay, this line 1 indicates the equilibrium reaction between iron to iron 2 plus, right? So what is the line 1? So line 1 indicates the equilibrium reaction between iron and iron 2 plus, right? Now after formation of iron 2 plus, it is forming iron 3 plus. So line 2 is indicating the equilibrium reaction between iron 2 plus and iron 3 plus, right? Now these two line 1 and line 2, these two line is parallel to this pH axis. Why? Because these reactions are independent of pH, independent of H plus. Iron to iron 2 plus, in this reaction H plus ion is not involved, so this reaction is pH independent. Because of that, this line, which is representing the equilibrium reaction between iron and iron 2 plus, is parallel to pH axis. Second line, line 2. Line 2 means the equilibrium reaction between iron 2 plus and iron 3 plus. Similarly, this reaction is also pH independent. Since it is pH independent, the line 2 will be parallel to pH axis. Line 2 will be parallel to pH axis because it is independent of pH. Okay. Now coming to line 3. Line 3 is a reaction between iron 2 plus and iron oxide Fe2O3. Now here iron is present plus 3 oxidation state, and here also iron is present plus 3 oxidation state. So in this reaction, so iron 3 plus to Fe2O3, this reaction, there is no transfer of electron. So if there is no transfer of electron, the reaction will be redox independent. If it is redox independent, so we will get the line parallel to redox axis, means potential axis. So line 3, which is representing the equilibrium reaction between iron 3 plus and Fe2O3, this line will be parallel to y-axis or potential axis. Why? Because this reaction is redox independent. Okay, now coming to line 4 and line 5. Line 4 is the reaction between iron 2 plus and Fe2O3. Iron 2 plus and Fe2O3. So in this reaction, so we can see there is a reaction number 4, there is H plus ion is involved. At the same time, in this reaction, oxidation number of iron is changing, plus 2 to plus 3. So this reaction is dependent to pH as well as redox. So reaction 4 represent line number 4, which is representing reaction 4 and indicating the equilibrium reaction between iron 2 plus and Fe2O3 in this reaction is pH dependent as well as redox dependent. Why it is pH dependent? Because in this reaction H plus ion is involved. And why it is redox dependent? Because here the oxidation number of iron is changed, right? So since it is both pH dependent and redox dependent, we are getting this slope line. Similarly, line number 5, where iron 2 plus equilibrium between iron 2 plus and Fe3O4. Here also there is a change in the oxidation state of iron. Here iron is plus 2, here is iron is plus 2.66. So oxidation number of iron is changed, and also there the reaction H plus ion is involved. So line number 5, which represented the equilibrium reaction between iron 2 plus and Fe3O4, this reaction is pH dependent as well as redox dependent. Since reaction 5 is pH dependent as well as redox dependent, we are getting this slope line. So in Pourbaix diagram, we are getting these 5 lines representing 5 different reactions. Okay, so first one, reaction between iron and iron 2 plus. Second one, iron 2 plus and iron 3 plus. Third one, iron 2 3 plus to Fe2O3. Fourth one, iron 2 plus to Fe2O3. And fifth one, iron 2 plus to Fe3O4. Right? So 5 lines, 5 reaction. Each line representing the equilibrium reaction between the component. Now in this diagram there is also 4 different zones. Okay, so first one, where iron is present in form of iron metal, it is called immunity zone. Okay, it is called immunity zone. Second one, Second zone is corrosion zone, which where iron 2 plus and iron 3 plus is present, corrosion zone. And when it is forming oxide forming zone, this green one, this is called passivation zone. Okay, so these are the three different zones. Okay, and here we are getting two dotted line. This is one dotted line, this is another dotted line. This is called actually oxidation of what? This is called this dotted line indicating two reaction, water hydrolysis reaction. In water, uh, during corrosion, this water we have seen that hydrogen evaluation reaction and oxygen absorption reaction. So these two reaction representing by these two dotted line, right? These two reaction representing in electrochemical corrosion, we have seen that there is a cathode reaction. In cathode reaction, there is oxygen absorption and hydrogen evaluation. So this is the oxygen absorption reaction, this is the hydrogen evaluation reaction. So these two lines representing these two reactions. So whatever I have discussed is written here, that is salient features of Pourbaix diagram. So Pourbaix diagram, the horizontal line between iron 3 plus and iron 2 plus. So everything is written here. Okay. So uh, this topic, this corrosion topic, from this corrosion topic, what we have understood? We have understood that every metal, whatever we have seen, is susceptible to corrosion. And there is a two different type of corrosion. One is electrochemical corrosion and one is dry or corrosion. Now dry corrosion, there are three different types: oxidation of corrosion, corrosion by other gases, and liquid metal corrosion. Now in electrochemical corrosion, I talk about the anode reaction where anode metal is corroded, and also I talk about that cathode reaction where hydrogen absorption, hydrogen evaluation, and oxygen absorption reaction. And finally, we discuss about Pourbaix diagram of iron. In this Pourbaix diagram, we discussed that how different oxidation state of iron is depending on pH, and how this potential, electrochemical potential, is changing with pH. In this diagram, we have 5 lines, 5 different reaction, and 3 important zones. One zone is called immunity zone, one zone called corrosion zone, another zone is called passivation zone. When oxide is forming, that is called passivation zone. When iron 2 plus, iron 3 plus is present, called corrosion zone, and only iron is present, called uh, uh, that is called immunity zone. Okay, so this is all about the corrosion. Okay, I hope that you have understood this corrosion topic. This is a very important topic for your BTech chemistry syllabus. Okay, thank you, student.